Thank you very much. It's a pleasure to speak to this distinguished audience. Today I will tell you about some recent work and as well as work in progress. Is there any way to mute this blip?
That's because you're co-host. Irene, you can remove that, I think, in the participants. So usually hosts get the ding dong whenever anybody shows up.
Yeah, I can remove
Yes.
it.
Thank you. So I will tell you about this recent paper that we wrote with Simon Caroniot, Damil Masach, David Simon-Zaffing, as well as some work in progress, but I don't think I'll get to the work in progress realistically. And as I understand, there's plenty of time for questions, so please interrupt me anytime. I really would like to make this as interactive as possible. So, so let me start with a really very quick motive. The blip is still there, and it's a little distracting, but I don't know if it can be removed.
I mean, I remove it from your main screen, but if I remove it from the iPad, then you cannot share the screen. So
okay.
No, hopefully people will stop joining soon. So
there's a way to remove it. I think for.
Okay, sorry. So the motivation will be very short, and it hardly needs to be emphasized for this audience. And it is the Swampland question, of course. What is the space of low-energy effective field theories that contain gravitons, mass spin 2 particles, and emit the UV completion? As you are very well aware, in fact, you invented and work on this subject. Both conceptual arguments, often having to do with black hole physics, and surveys of the string theory landscape suggest some very interesting, very plausible, and probably true conjectures about some criteria that make an effective field theory either part of the swampland or part of the honest landscape. However, I think it's fair to say that many of these conjectures have not been proven, and some of them are not really fully quantitative. Even something like the weak gravity conjecture comes with an order 1 numerical coefficient that appears to be model dependent, and one would really like to do better and have a more definitive and sharp criterion to distinguish which effective field theories are part of the swampland and which are not.
Leonardo, sorry.
What comes to mind to someone with my background is, can we apply the bootstrap paradigm? So you're probably familiar with the fact that in conformal field theory, we have been able to really put sharp boundaries between in the space of putative conformal field theories defined in terms of critical exponents and NOP coefficients. There are these famous exclusion plots. This is something that the conformal bootstrap is very good at doing. It's putting sharp boundaries between something which is definitely excluded and something which may be allowed. And here, to illustrate this idea, I have this cartoon of the Baron and Munchausen, who was the original bootstrapper. So the metaphor of pulling yourself up by your bootstraps actually has this antecedent in the fact that Munchausen was actually lifting himself up by his pigtail from the swamp. And so the idea is then, can we actually get out of the swamp using the bootstrap? Now, if we are looking at quantum gravity in asymptotic anti-de Sitter space, then of course the reference to the conformal bootstrap is really quite appropriate because more or less by definition, quantum gravity in anti-de Sitter space is a conformal field theory on the boundary. And so the bootstrap, the Swampland program in IDS really is just a corner of this conformal field theory bootstrap. And if we want to have something that resembles Einstein gravity in the bulk, then we should have a large number of degrees of freedom that makes the theory in the bulk weakly coupled. And furthermore, to suppress higher derivative correction, there is this general law, which is not really being fully proven, it's something we would like to do, that to suppress higher derivative corrections, you also need a large gap between, say, the stress tensor operator and the first single trace primary operator. So this will really be the matter of a second talk when our paper finally comes out. Today I will focus instead on asymptotically Minkowski, where the tools are similar. In fact, we are inspired by the conformal field theory bootstrap, and we will instead use the general rules that govern the scattering, ideally of gravitons, although today, for technical reasons, we will stick with external scalar particles. And the idea is to input very general assumptions about analyticity and boundedness of the S matrix of scattering of gravitons and see how far we can go. I want to emphasize in this introductory slide that whereas in the CFT case, all the axioms are quite rigorous, and in particular, certain boundedness properties of correlators just follow from convergence of Bernoulli-Prout expansion. The story is a little more speculative in flat space. So nobody has actually fully derived the axioms that the S matrix should obey, certainly not in a theory of quantum gravity, and even without dynamical gravity. Although this is an ancient subject, there still is some uncertainty about how to derive even what you thought may be completely sacred property of the S matrix from first principles. So I will emphasize that in a minute. Okay, so just to put this into some context, of course, it's been known for a long time. There's this famous paper by Adams et al., but I'm sure that the story was also known, at least in its generalities earlier, that even without dynamical gravity, what appears to be a perfectly healthy Lorentz invariant local effective field theory may not have a UV completion. And low energy couplings in an effective field theory obey interesting positivity constraints. So if you look at this paper that I'm citing here, you will see, for example, in the scalar 4-point coupling, the leading higher derivative irrelevant correction with 4 derivatives is constrained to be positive. And if it's not positive, then you have a violation of unitarity and causality at high energies. And this idea has been put on very systematic footing in recent months, I would say. Nima Kanihamed and collaborators have worked on this for years, and a long paper came out recently. And I will in particular emphasize these 2 papers, which were a direct inspiration for our work. In fact, of course, Caron Yuat is one of our collaborators. And I will mention what's special about this paper. What these papers did, they were able to derive for the first time 2-sided bounds for the higher derivative terms in effective field theory, both a lower and upper bound. And so the idea then is to apply this general program, again, use very general consistency principles about scattering of gravitons to the Swampland question. Are there any questions about the general idea?
Leonardo, can I ask a question?
Yeah.
So if we're speaking of gravity in 4 dimensions, how do you handle infrared divergence?
Yeah, we will not. So the entire talk will be in d greater than 4.
Okay.
Although of course I will hopefully comment at the end about what you may try to do in 4 dimensions. But yes, absolutely. In 4 dimensions, the scattering of graviton is really not well defined. There are infrared issues, and so I mean, roughly speaking, you can either work with dressed gravitons or attempt to define some more inclusive infrared safe observable, and then you have to rethink the axioms of the S matrix in that context.
Mm-hmm. Right.
Okay, so still as an introductory slide, let me schematically enunciate the issue here. So of course, the first thing you really want to do logically and would be to start with the theory of pure gravity, in other terms, an effective field theory that, as we know from Weinberg's work and long ago, a low energy is the only consistent consistent interacting theory of spin 2 particles is Einstein general relativity. And then, of course, there may be higher curvature correction, which I'm here indicating schematically as this higher curvature terms. And here, again, I'm being schematic. There are multiple structures, but I'm ignoring those details. And this being an effective field theory, of course, it's a low energy expansion that is valid for energies much smaller than some UV cutoff, which I will always indicate by the letter big M. And of course, the UV cutoff is necessarily smaller or most equal to the Planck scale, but it may well be much lower. And a classic example where that is much lower is of course, weakly coupled string theory. In weakly coupled string theory, if you're scattering massless string states, supergravitons, then of course the scale at which you encounter new physics is the threshold for production of massive string states. So the UV cutoff is the string scale, which is of course much smaller than the Planck scale, which comes with this parametric suppression by an inverse power of the string coupling. And this is actually the situation that we will really be able to address systematically. The situation where we will assume that we have an effective field theory which is weakly coupled, in the sense that you can trust the 3-level expansion plus small corrections of the effective field theory all the way up to the UV cutoff. Then, of course, eventually, at energy much larger than the UV cutoff, the theory becomes strongly coupled. And again, if you get confused, keep in mind the canonical situation of weakly coupled string theory. We consider that the string coupling is fixed, but let's say very small, 10 to the minus 12. And then there's no doubt that all the way up to the string scale, you can certainly trust the 3-level approximation to string theory, but eventually, of course, as you reach the Planck scale, it's going to start producing black holes, and the whole thing becomes very strongly coupled. Now, the question you want to address is to make precise the general intuition that we have, since time immemorial, or at the very least since Wilson, that these higher derivative corrections really should be of order 1 in units of the UV cutoff. And so ideally, you like to put sharp numerical bounds that will tell us precisely how these coefficients should behave as inverse powers of the cutoff. And again, it would be unrealistic to be able to put a bound of these coefficients as inverse powers of the Planck length, because we have, as I just emphasized, the counterexample of weakly coupled string theory, where these coefficients are much larger. They scale with inverse power of the string length. Okay, so of course this was studied and set up, and in fact we're in this beautiful paper by Camagno et al., who actually were able to show that precisely in this situation that I emphasize, where we have a weak coupled theory of gravity that, however, can have large 3-level higher derivative corrections, then very much not anything goes, and these higher coefficients are indeed suppressed. And they showed this by finding that if they're not suppressed, then you violate causality. However, in their work, they were really not be able to pin down the precise numerical coefficient. They really had just some more qualitative argument about causality violation that just gave you the parametric suppression.
Sorry, Leonardo, can I ask a question?
Yes.
So this argument by Camagno, etc., it's also in dimension strictly bigger than 4. Does it have the same problems that you and she were just discussing?
I think they were somehow able to also make statements in 4 dimensions, but it's a little more tentative in my understanding.
Okay. Thanks.
Yeah, so what did you mean by, what is the coupling that's weak? You said in a weakly coupled theory, the coefficients are very small, or did I mishear you?
The coefficients are very small. So the precise statement is that the coupling at the cutoff scale is small.
What is the coupling in this theory?
In string theory, it's a string coupling.
Oh, in this, I thought you were talking about this theory of pure gravity, or?
Oh, it's a Newton's constant. I have the Newton constant in front.
But that's I thought you were talking it's much smaller relative to the
Yes,
Newton.
but I've been very precise. In units of the UV cutoff, at the UV cutoff, so we're doing effective field theory. Right, so the theory is weakly coupled at the scale of the UV cutoff.
Weakly coupled, you mean gravitationally weakly coupled?
All see, the way I've written this down, there's an overall coupling, and then all the other couplings are expected to be of order 1 in units of the UV cutoff. I will be a little bit more precise in a minute. But again, string theory, if you get confused, think about string theory. All interactions in string theory are proportional to one dimensionless coupling, which is a string coupling.
Right. And what are the dimensionless couplings here? You mean like alpha 2 and alpha 3, or that's what I'm confused about?
Well, alpha 2 and alpha 3 are obviously not dimensionless, right? You compare R with R squared, so alpha 2 scales like 1 over m squared.
I just didn't see in this action you wrote down a dimensionless coupling constant. That's sorry, it's a very basic question. So what do you mean by weakly coupling?
Dimensional analysis, right? So so there is a scale big M. Make everything dimensionless using big M. So what Wilson told you is that if you make coupling dimensions using big M, you just generically expect them to be of order 1.
Okay, thanks.
That is what we would like to prove and put a precise numerical bound on that order 1 coefficient. Is this clear?
Sorry, Leonardo, well, how is big M actually defined? Is this defined based on the...
I will be very precise about this in a minute, but again, in string theory, there's no doubt how this is defined. It's the mass of the first exchange massive mode. Okay, so all right, so of course so we are warming up to doing this in dimension greater than 4. This is actually straightforward, but of course you have to deal with polarizations of the external graviton. So as a warm-up, we will do something a little simpler. We will consider a massless scalar coupled to gravity. And of course, we're just looking at this from the viewpoint of effective field theory. So the effective field theory only includes this massless scalar and the graviton, and then it's valid up to some UV cutoff big M, and above big M, anything could happen, really. We are going to be completely agnostic about what happens at higher energies, except, of course, for very general principles such as unitarity and causality. And so, since I've emphasized, I'm going to treat the theory as weakly coupled all the way up to the cutoff scale. Then it's permissible, at least to leading order, to treat the low energy expansion for this 2-2 scattering process at 3 level. And so here I wrote down, of course, this term here is just the graviton exchange at 3 channels. So this would be square root G, square root G. These other terms here are, if possible, there may be, of course, scalar self-interactions. And given uniqueness of the 3-level on shell couplings of 2 scalars and 1 graviton, this is the only term you can write, etc. And then everything else has to be analytic in an expansion of the Mandelstam invariance. So we have S plus T plus U equal to 0. And so you can quickly convince yourself that the only terms you can write down are of the form, of this form. And so you write an infinite sequence of terms of this kind. Okay, so that's the more general form of the 3-level effective field theory expansion. And here, the subscripts of this coupling is related to the dimension. And so, G2, of course, is multiplied by something of n to the 4, G3 n to the 6, etc. Now, and this is clearly the only fully cross-systematic terms you can write down. The precise statement here, since there are questions about this, we are really assuming that we have a whole family of S matrices with some coupling epsilon, such that all interactions are proportional to epsilon. And we have written the leading order expression as epsilon goes to 0. Again, keep in mind string theory where epsilon would be the string coupling. And of course, we could systematically correct this adding low energy loops. Low energy loops will introduce cuts that, since this is a massive scalar, will go all the way down to the origin in Mandel space. And then, so in other terms, we will insist putting bounds on shell quantities. So there will be an actual scattering experiment that you do on shell, and how you match that the strength of that scattering process to a coupling in the Lagrangian. Of course, it's a matching procedure that you can do at 3 level. If it's sufficient for your precision, you can correct it at 1 loop, etc. But that's really just part of the matching process. And since I'm assuming that the theory is weakly coupled all the way up to the cutoff scale, it's the first approximation, just the 3-level matching. Okay, so here I'm repeating again this example of string theory. I think I've emphasized that enough. And then the question now is, now that I've made it quite precise, what can we, so there's an overall epsilon that, of course, I have no hope of controlling, that's just overall. But what I can hope to control is ratios of couplings. The ratio of these higher derivative couplings with each other and with the Newton constant is something that I can hope to control. And then, of course, given that these are dimensionless quantities, I need to pull out the suitable power of the UV scale M. And once I've done that, finally, I hope this answered the question that was asked earlier. Then now, finally, we can write everything in terms of truly numerical dimensionless coefficients, CK. And the idea is, what can we say about these CKs? Right. Now, the Swampland question here can now be stated very precisely. What is the allowed space of, in this space of dimensionless coupling that is consistent with the theory having a UV completion?
Leonardo, can I ask a question here? So in the example, in the easy scalar example you were just describing, the scale M could have been also the scale at which you have a field theory completion, right? And your arguments were somehow insensitive to this, right?
So yes, M is a UV cutoff. In this particular setup, big M truly is just the mass of the first exchange massive state. Mm-hmm. Because if you are doing things at 3 level, then big M literally is the scale of new physics, right, precisely defined as the pole or at the first massive state.
But I'm just trying to understand. So the bounds that you're giving, for instance, I could also apply to a low energy quantum field theory.
No, absolutely. Sorry. Of course, this is in fact what was done before, and our novelty is that we incorporate gravity. So as I will explain in a minute, incorporation of gravity is quite subtle, and you cannot just open the recipe book and couple to gravity. You need a bit of a new idea. But absolutely, if you set the Newton constant equal to 0, as I will review in a minute, then this was done in the papers that I cited earlier.
So, Leonardo, can I ask you about this lambda 4? So yeah, you are allowing a 5/4 coupling, but wouldn't the perturbative RG already tell you that the low energy limit will not look like lambda 4, but lambda 4 over log S, something like that?
Yeah, as we will see in a minute, in fact, I allow this just for completeness, but we will be able to say absolutely nothing about these couplings, because in order for us to be able to write down a dispersion relation, we'll have to do some subtraction. So the subtraction will completely kill these terms. So
okay, but I'm just saying that the unitarity already tells you, the unitarity and analyticity already tells you that it can never look like lambda 4 by itself, but lambda 4 over log S.
I completely agree. I completely agree. But yes, the reason I wasn't very careful here is that actually these terms will completely drop out from the analysis.
Okay.
Okay. So
I have another question quickly.
Yes.
So I maybe missed it, but I guess, did you say that the M is defined as the first pole that you haven't, of the state you haven't included in your EFT or something like that?
Yeah, I will be a little bit more precise in a minute, but yes.
Okay.
At 3 level, big M will literally just be the first pole.
Yeah, and Leonardo, how do we know there are no other log terms in the other powers, on the higher powers?
So generally, at the full non-perturbative level, the story will be complicated. But what we do know is that there is a systematic expansion, such as for epsilon goes to 0, this is the leading order approximation. And then, yes, absolutely, there will be logs that in fact will certainly correct these terms, but they will come with this coupling G squared. And think again about string theory. Yes, there will be a correction, no doubts about it. But if G string is 10 to the minus 12, then those correction will be 10 to the minus 24. You could systematically correct them, and it's an interesting question to correct them, but it's a little bit besides the purpose, because again, it's a very small correction by the assumption that theory is weakly coupled all the way up to the cutoff scale.
So it doesn't affect your conclusions.
It does not affect the conclusions. Okay,
sorry, can you just to be sure, maybe I'm jumping ahead, but are your bounds on these ratios going to be just asymptotic bounds in the limit of weak coupling, or are you going to be able to?
The precise numerical bounds will be asymptotic limits in the limit of weak coupling.
Okay.
And then of course you could systematically correct them in expansions in epsilon. Okay, so now, of course, the idea is to use some sort of S-matrix bootstrap approach, and so we need to clarify what property we expect from the S-matrix. So the one that I would say is rather uncontroversial is that the S-matrix better be unitary. And so here I'm writing the S-matrix as the disconnected piece plus the amplitude M. And of course, just a little bit of trivial kinematics. So we are scattering part 1 and 2 going to 3 and 4. There's a scattering angle theta, and in our conventions the cosine of theta is written in this fashion using the Mandelstam invariants U and S, and of course S, remember we're scattering massless. By the way, the fact that the scalar is massless is for simplicity. You could of course add a small mass compared to the UV cutoff, and the analysis will go through almost identically, just a little bit more complicated formulas. And then for the cosine of theta to be between -1 and 1, then U has to be in this range. And this is the physical region for S-channel scattering of Mandelstam variable S and U. And then, of course, S plus T plus U is equal to 0, so you can compute T. And then to express unitarity, the quickest thing to do is just take the imaginary part of the amplitude. Given we have crossing symmetry exchanging 1 and 2 and Bose symmetry, then the sum is only over the even spins. And then just from kinematics.
Ой, не могли бы вы прислать на WhatsApp слова? Просто потеряли мы.
There is some disruption.
Perfect, sorry.
And then just from kinematics, you're going to have a suitable polynomial of cosine of theta. This is in 4 dimensions to be Legendre polynomials, in general dimension should be Gegenbauer polynomials. And then the entire dynamical content is then captured by some density, rho j of S, that all we're going to say about it, the unitarity constrains it. In our normalizations, unitarity forces this density to be bounded between 0 and 2. And you see, I put in blue here the lower 0 bound, because actually we will not use the upper bound 2. The reason we will not use the upper bound 2 is because we're assuming the theory is weakly coupled. So rho is really small, is infinitesimal. So always away from saturating unitarity at the upper region, but it will be important for us that this density is positive. Okay, this is, I would say, is rather completely uncontroversial. What requires a bit more discussion are the analyticity and boundedness properties of the S-matrix. So these are the properties that would be completely rigorous in the CFT context, but they're not really fully established in quantum, as far as I understand. Even without dynamic of gravity, some of these properties are not really fully established, even in gapped ordinary quantum field theory, although some of them are. And so, so this is the complex S-plane. So the first assumption that we will be making is analyticity away from the real axis. In fact, this is actually, so if this is my, so UV cutoff M. So of course, generically here, there will be a cut that starts here, and then there will be a cross cut here as minus M minus U, the T-channel cut. And then you could have a bunch of, in our case, of course, we just have the poles from the massless graviton and the massless scalar. If we were including higher loop corrections, there would be additional cuts that go all the way down to the origin. And so actually, in that situation, our arguments would go through if we just assume analyticity in this kind of a region. In the three-level approximation, the amplitude will be analytic everywhere away from the real axis. So I would say this is an assumption we make. I would say it's not a terribly controversial assumption. Crossing symmetry is also pretty safe. For 2-to-2 scattering, crossing symmetry actually has been established in the framework of axiomatic quantum field theory, at least for gap theories. For higher scattering, actually, curiously, it's surprisingly hard to prove crossing symmetry. There was a recent paper from a postdoc at IIS inspired by some conversation with Witten. But for 2-to-2 scattering, I would say crossing symmetry is under control. And the one final assumption, which really requires a bit more discussion, is we will assume that in the Regge limit, by which we mean we take fixed U is the momentum transfer. So for fixed momentum transfer and large energy, we're assuming that the amplitude over S squared goes to 0 along any ray. If you go to 0 in the upper half complex plane along any phase, then we are requiring this to be 0. So I'm going to comment on this in a minute, but first I want to know if there are any questions.
So I have two concerns about this. One is that I suppose you are taking the weak coupling limit, and then you speak of the large S limit. The order of limit, potentially one has to worry about the order of limit. So what do you mean here?
So again, the theory will certainly become strongly coupled for sufficiently large S. Otherwise our entire analysis would be trivial.
Okay, so here on this slide, by M, you mean the non-perturbative amplitude.
Sorry, can you repeat?
This big M here is the non-perturbative amplitude.
This big M here would be the non-perturbative. Absolutely. Sorry, I was confused with, curly M here is the full non-perturbative amplitude. Mm-hmm. So, okay. So we are in the full non-perturbative setting. We will split the amplitude. Of course, in the full non-perturbative setting, but anyway, let me just say these the words. In the full non-perturbative setting, we split the amplitude in low energy piece and a high energy piece. The low energy piece you compute by effective field theory. And it is there that we will make the approximation of three-level. I don't think it's a big deal. You could correct that approximation order by order in this epsilon expansion. And given that the amplitude is weakly coupled all the way up to the cutoff, that's a small correction. The correction is not small at high energies. And in high energy, we will make no perturbative assumption whatsoever. We will just use very general properties as outlined here.
Sorry, Leonardo, I'm a bit confused. The condition 2, you're taking S to infinity.
Yeah.
And the region you have cut off is bigger than S equals to M, you're out of your range. So what do you mean?
Sorry, can you say it again?
You have a cutoff M.
No, absolutely. The cutoff M is the cutoff where the effective field theory is valid. So
no, I know, but so your amplitude MSU doesn't make sense beyond that, right?
No. M is the full non-perturbative amplitude.
So you're willing to, so you're going beyond the region that you're actually considering in your
absolutely.
discussion.
So the whole point will be there's something that we in principle is calculable, is the low energy expansion. And then there's something which is not calculable, which is the high energy behavior of the amplitude, but which will be completely agnostic, except saying that it has to obey general properties.
Oh, okay.
And then the question is, what what do those general properties imply
Oh, I see.
for the low energy expansion?
So this too is going to be very important for you then. I guess.
Yes. Yes.
Thank
So of course this requires a bit of a discussion.
Can I
Yes.
ask another question?
Yes.
Again, about this point number 2. So, I mean, in the context of local quantum field theory, the proof of this I've seen starts with polynomial boundedness, and then you go through the first order bound, and from that you derive the twice subtractive dispersion relation.
Correct.
In gravity, the first order bound is expected to fail. So, is there any sort of argument why this should be true in gravity?
I'm coming. This is the content of my next slide. But indeed, so as she's saying, in fact, in the first order bound is actually stronger than this. It's just something like S log square S in 4 dimensions. And so the first order bound certainly implies this behavior. But in the case of gravity, you are on less firm footing. And so let me make some comments about this. First of all, there's been some recent papers that have studied this conjecture in the context of classical theories of gravity. And in fact, this has been promoted to a principle that any consistent three-level theory of gravity should not grow faster than S squared. In fact, pure gravity itself, you know, we can go back to the graviton scattering here. For fixed U, clearly this grows like S squared, right? So the graviton scattering precisely saturates this S squared behavior. And from the get-go, we are not allowing that to be a possibility, okay? So we need to require something which is a little better than S squared, because we actually need this to go to 0 for large S. Of course, this is exactly what happens in three-level string theory. The fact that the graviton comes accompanied by a whole Regge trajectory of higher spin particles softens the high energy behavior a little bit. And so if you work in the physical region, where remember U is negative, the realization of the graviton precisely gives you something which is within our bound. Now, why should this be
Sorry,
true?
but this is for perturbative string theory, but if you go enough to the UV, wouldn't you like create black holes and all kinds of stuff?
You will create all kinds of stuff. And
so what do you think of this?
So I have 2 bullet points here. The only thing I can say, which is heuristic, yes, you will create all sorts of stuff. And in fact, if you are naive and you write down something like this, this black hole ansatz, you will find that there's an exponential piece that decays, you know, for an exclusive process, of course, black holes are very suppressed in physical region, so it will be something which is exponentially suppressed for large energy. But of course, the moment you continue that to positive imaginary part, that exponentially suppressed piece has the danger of being exponentially increasing. I think that's crazy, right? I mean, physics really tells you, as she was mentioning earlier, this idea that there's actually this very nice discussion in the Kemp's paper about a black box signal model. You input a signal and then you do the Fourier transform and see what causality and unitarity imply for the Fourier transform. And on very general grounds, you should really be able to argue that causality tells you that the amplitude better be analytic in the upper half complex plane. Another physical argument is by transforming to impact parameter space, which I will review in a minute. And again, look, it's possible that quantum gravity is totally outside the realm of quantum mechanics. I doubt it. And so heuristically, you really should expect that even the scattering of gravitons should be analytic and bounded in impact parameter space. Now, again, this is an assumption. If you don't buy this assumption, then you can construct your own version of quantum gravity that does not obey these assumptions. I think they're physically well motivated. And ideally, one day they will be derived by taking the flat space limit of ADS. And so that's my point. That if you actually regulate the theory, by putting it in this beautiful box, which is ADS, then these are perfectly rigorous bounds, because they follow from the conversion of the operator product expansion in conformal field theory. In fact, the non-perturbative Regge bound in conformal field theory is actually much stronger. It tells you that the growth should be just S. And so, of course, there's many people that study this, and it hasn't really been turned into a theorem. But the idea is that you should start in ADS, where the story is perfectly well defined, and somehow carefully take the limit, and hopefully derive this more general bound. But of course,
one could argue though that the flat space limit of ADS it's not like some kind of simple continuous limit where you can just move.
These are all legitimate objections, and if you don't believe this assumption, then I have really nothing else.
Okay, I just wanted to.
These are my axioms. I think they're very well motivated, but we will derive bounds based on these axioms.
Okay, thank you.
I have a quick question about that.
Yeah.
You mentioned causality, which of course is related to analyticity, but I missed how that's related to the S squared.
How is that related to the S squared? So in the simple context of in ordinary quantum field theory, even simpler in the context of just quantum mechanics and causality, then you can split this into two parts. First of all, causality tells you that the amplitude should be analytic in the upper half plane and polynomially bounded. It cannot grow faster than a polynomial. If you then further input unitarity, you find that the amplitude is actually bounded by, the modulus of the amplitude is actually smaller than 1, which by the time you rephrase in the context of quantum field theory will give you basically these twice subtracted dispersion relations. So in the context of ordinary quantum field theory, I would say this is all rather well motivated. For quantum gravity, it's a postulate. I would say so okay, this might depend on your personality, perhaps, or on your prejudices. I think what we have learned, what string theory has taught us, if anything, is that quantum gravity behaves in a much more conservative way than some wild people have speculated. Black hole evaporation is unitary. So the underlying philosophy here is that the scattering of gravitons really should obey some general axioms, not too unlike. That doesn't bring you as much outside the ordinary framework of scattering in quantum field theory. But I believe string theory certainly is in this category of theories.
Very quick question. So you said that this is proven in ADS. Is this in any
dimension? Yes, in ADS it's a consequence. In ADS, I'm taking ADS CFT as a definition. So I'm defining quantum gravity in ADS via the boundary theory, and then in CFT this is a theorem.
For any dimension.
In any dimensions, yes.
Okay.
Leonardo, can you sketch how the S in ADS might turn into S squared in flat space?
Oh, sorry. The point is that the S bound is the bound that is correct at fine N.
Right. So I'm wondering, sort of, if you're using that, then what you have in mind, or why not you're using the other one?
No. In ADS, the non-perturbative finite N bound is S. Mm-hmm. The leading tree-level or leading large N behavior is actually S squared. That's the chaos bound.
So why didn't you use that as a
chaos bound is actually precisely the order of S squared, but the chaos bound is an artifact of taking the larger limit too fast. If you actually look at the non-perturbative theory for finite N, then the bound is better. So you could say similar words about the behavior in non-perturbative quantum field theory. In non-perturbative quantum field theory, without gravity, the bound is better than S squared. It's something in 4 dimensions, it's something like S log square S. Okay, so
sorry, but, about this point, but when you actually take the flat space limit starting from ADS, you do have to take large M, but you also do not want to stay in a TOF limit, right? So
yeah, I mean, look, I have not done it, right? So the all sorts of possible subtleties that could hit you here. Again, I mean, I could try to sell you this a little bit harder, but the truth is this is a postulate.
Okay.
So our analysis will work for quantum gravity theories that have this behavior. I certainly think the string theory is one of them, but okay. So okay, so then let me explain the key idea next. Well, the key idea, of course, is that given that we have this analyticity and boundedness properties, we get to take this non-perturbative amplitude M, do a big circle. We need to divide by powers of S, because remember, it's only M over S squared, which is going to 0. So here there's, you see, in the denominator, I have K powers of S prime. And so I get a sequence of some rules. The smallest value of K, which is consistent with this converging at infinity, is K equal to 2, because for K equal to 2, I have 2 powers of S prime. And then clearly this is 0, because I pull this to the outer at infinity. And then the idea here, the main idea of the whole thing, is that we're going to split this 0 into 2 pieces. There is a low energy piece where I can use the parameterization from our low energy expansion, where the assumption of weak coupling is justified. And then there is a high energy piece that strictly at when the energy is M squared, it's still weakly coupled, but eventually will become strongly coupled at energy much smaller, much bigger than M. But I don't really care, because I will be completely agnostic about what happens at high energy, other than imposing unitarity. And so that's the key idea. The connection between the low energy expansion and the high energy behavior comes from a dispersion relation. Now, another small technical comment. Rather than just dividing by a power of S prime, we divide more symmetrically by a power of S prime times S prime plus U, because remember, we want to preserve S going to T crossing symmetry. And so this choice preserves S to T crossing symmetry. And moreover, we want to do so in a way that doesn't introduce any extraneous mass scales. So then this is the only choice that will be both crossing symmetric and doesn't introduce any additional scale. Okay, then.
Sorry, Leonardo, in this picture, you have already ignored the massless loops, the branch cut using massless loops.
In this picture, I've already ignored the massless loop, but it would not be difficult to include them, right? You'd in addition to these low energy poles, there will be low energy cuts. This expression will still be valid, but then the matching with the low energy parameters would be a little bit more involved.
Okay, but is that going to allow you to derive, in principle, some actual inequality that corrects the whatever bound you're going to derive?
I think so, in an asymptotic sense, right? So you're going to have a power expansion in this parameter epsilon, and so long as epsilon is small, I mean, the idea is, again, in the full non-perturbative setting, you have to tell me what the meaning of the coupling is, right? You have to set up some scattering experiment, some on-shell scattering experiment that measures that coupling. And then you could actually derive perfectly rigorous inequalities for that coupling. How to match that with the actual parameter in the Lagrangian is a little bit of a less urgent issue, but if you want to do it, then you could do it in a loop expansion.
The one thing that worries me a bit is, before you say that this weak coupling approximation is supposed to be valid for energy much smaller compared to your M, where
no. The low energy expansion is valid all the way up to M, not much more than M, all the way up to M. So okay. Think again about string theory. If at the string scale, if the string coupling is very small, it's perfectly consistent to look at string 3-level scattering. There's nothing strongly coupled at the energy of the first massive string state.
Okay.
It's only for energy much bigger than m then you will encounter strong coupling. Okay, so then you take this and do a little bit of algebra. And again, there is a low energy piece where you input the low energy expansion, there's high energy piece. And the high energy piece, we're going to write it in this very generic way. So remember, we had this rho j of S, which was our unknown density. So we define a average weighted by this rho j of m, sometimes some kinematic factors. And the point of the average is little m is a dummy integration variable. It's the variable that tells us how far we are in the high energy cut. And j is also summed over. So this bracket here, there's an explicit dependence on little m and j, but remember, these are really just summed over. And so the way so here is an example. The simplest sum rule, the one for k equal to 2. The low energy contribution, you pick up some poles and you get an expansion that contains this parameterization of the low energy couplings. And that, of course, goes on forever. And then on the right-hand side, you have something which you evaluate at high energy, about which you are agnostic, either on the fact that this is a positive average. And again, little m and j are summed over. And so the left-hand side depends on a variable u, which is arbitrary. Well, not quite arbitrary. U is between minus m squared and 0. So you fix u, and you have an expansion in terms of these low energy parameters equal to something that is written as a very precise combination of these polynomials weighted by u and m, where little m is summed over. And all you really know about these averages is that they're positive. Okay, is the logic clear? So you have this very, as it turns out, very constrained sum rules that relate this low energy expansion to something which has to be positive at high energies. And the nature of these sum rules is that the higher k sum rules only depend on the higher couplings, So C4 only starts with G4, C6 to start with G6, etc. And the graviton only is an issue in the first sum rule. Okay, so okay, so this is we were certainly not the first to write down this kind of sum rules, but we were the first to understand how to extract some physics from it, because what people were very confused about before is this divergence that comes from the graviton pole as u goes to 0. Now you could say, well, why don't you subtract it out? After all, it's just the graviton exchange. So who can forbid you from taking this curly m, subtract the graviton exchange, and derive a dispersion relation for it? Well, what prevents me is precisely the assumption that I'm making that the amplitude should go faster than s squared for large S. The graviton propagator goes precisely like s squared. So if I were to subtract the graviton exchange from curly m, then I would not be able to derive a dispersion relation. And this is the obstacle that has prevented people from making progress. It's a technical thing, but that's the main point of our recent paper. Okay, so before dealing with gravity, for simplicity, let me review very briefly the
Sorry, Leonardo.
Yes.
Let me just interrupt so it's been 1 hour roughly now, and the whole thing is typically around an hour and 15 minutes. We have lots of very interesting questions, so that's good. But I'm just letting you know so that you keep it in mind. Okay. And also I'm asking everyone to if you have a very pressing question, then ask it. By all means, ask it. But otherwise, maybe we can keep on discussing over Slack.
Okay. Now let me review quickly how this would work without gravity. So without gravity, if you don't have this pesky issue of this thing divergence for u goes to 0, then there's an obvious thing you can do, which is do a Taylor expansion in u. Clearly, you have infinitely many sum rules because you can Taylor expand in u, and the simplest ones are this, G2. So from here, you instantly find this famous constraint that was in the original paper by Adams et al. That G2 is better be positive. From this sum rule, you instantly find the constraint that G3, well, better be smaller than, given that this is a negative quantity, G3 is smaller than 3 over m to the 6. And given that little m is, of course, bigger than big M, I can rewrite this as 1 over little m squared, 3 over m to the 4th, which is equal to 3 G2 over m squared. So this is a one-line derivation of a first equality that tells you that G3 and G2, by the time I pull out the suitable power of the UV cutoff, scale as they should. Now G4 can be computed in 2 different ways, and that's actually interesting because it gives us a constraint that just must be obeyed by the high energy data on their own. Although we are quite agnostic about the high energy physics, the high energy physics is absolutely not arbitrary. Unitarity and causality tell us that the high energy data can do complicated things, but always in a way that an infinite set of some rules of this kind should be obeyed. And so I just did it for you on the fly how these are true, but with a bit more work, using the null constraint, you can now actually also derive you see, the upper bound of G3 was obvious because this term was negative. But it turns out that because of the null constraint, this cannot actually be too negative. And so there's also lower bound on G2, which you can derive by doing a little bit of a linear optimization. And so you also find a precise lower bound on G3. And so all in all, you have two-sided bounds for this low energy parameter with precise coefficients. Okay, this strategy fails. So there are several issues about this. So dimensionality ends up working, but in a somewhat mysterious way. It's a little unclear why it is that things were scaling with the correct power of big M. The more practical issue that invalidates this expansion in the case of gravity is that there's a divergence. And then, although I'm doing this at tree level, it's also clear that if I were to incorporate these low energy loops, there will be cuts, there will be a log of u, and then it's very unclear what you do with log of u as u goes to 0. So it turns out there's a common physical resolution to do these issues, which is to measure effective field theory couplings rather than in expansion for small u, by doing a Fourier transform to impact parameter space and measure them at small impact parameters. So I'm going to explain this in a minute, but that's essentially the punchline of the talk. Okay, so what is impact parameter? So let's do a little bit of trivial kinematics. So we are interested in the Regge limit. So it's the limit of fixed momentum transfer and large energy. And then, as you're I'm sure familiar with, the scat. So u can also be written as minus e squared minus 4 e squared sine squared theta over 2. And so in the limit in which u is fixed and e is large, then the angle is small. And this we're also going to write as minus p squared, where p is the momentum transfer. And again, if you think about it for a minute, in this scattering process, the angle is very small. And so there is a line of, so we are in big D dimensions. One dimension is time. So then there's the line of scattering dimension. Then there is D minus 2 transverse dimension. And in this limit, the momentum transfer is in the transverse directions, as you can easily convince yourself. And then what is impact parameter? By definition, impact parameter is a vector in this transverse space, which is just defined to be the Fourier conjugate to the transverse momentum. So we're doing quantum mechanics, so we can choose to have either momentum eigenstates or position eigenstates. And so we take momentum eigenstate in the direction of head-to-head collision and position eigenstates in the transverse directions. That's the impact parameter. Okay, impact parameter is Fourier conjugate to transverse momentum. And as you can see, not surprisingly, this representation is sick in 4 dimensions because the two-dimensional Fourier transform over 1 over p squared diverges logarithmically in 2 dimensions, and 4 dimensions have 2 transverse dimensions. So we will restrict to the greater than 4. So what is the idea? So the physical intuition will come from doing things in impact parameter space, but in some sense, you know, if you hate physical intuition and you just want to do math, here is an infinite set of exact sum rules, which are valid for each value of u. The naive thing to do is to Taylor expand in u, but in some sense you can say, well, who forces me to Taylor expand? Let me just convolute these functions with, let me do an integral with some function of u on both sides, and let me choose a suitable function of u that extracts some physics out of this sum rule. Why not? So which function should we choose? Well, the first issue that you may want to address by doing this convolution with a function of u is that on the left-hand side, you really have these infinitely many couplings that contribute. And so you get a little nervous because the moment I do an integral with a function of u, I will have infinitely many couplings, whereas I really want to derive precise inequalities, let's say for the first few of them. So the first fix, which is a technical thing, but is a very useful one, is that you actually can improve the sum rules by purifying them. You see, the second sum rule starts with G4. So if I take a suitable linear combination of the two with suitable powers of u, I can actually remove this term. And I can keep going till I find a better and improved sum rule that only depends, for example, this is just an example, on the first 3 couplings, on the Newton constant, on G2 and G3, at the expense of making the right-hand side a little bit more complicated. And then what is the idea of deriving bounds? Well, the idea of deriving bounds is that you do not want to screw up the positivity property of the right-hand side. So you want to concoct a function f of p such that when you integrate it against the sum rules on the right-hand side, it's actually positive everywhere for each value of the spin and for each value of the sum integration value to m. Well, if that's true, if this is true, then of course, if this is positive for little m and little j, even the average will be positive. And by taking the average, I prove that the left-hand side is positive. And so, fortunately, these functions are plentiful. And so by playing with these functions, we actually get to impose inequalities on the low energy coefficients. And here is the connection with the physical picture I had earlier. It actually beautifully turns out that if you take in this sum rule little m large, compared to the cutoff, then something cute happens. There's a delta function that comes from the integral representation, and for large m, actually the spin localizes to little m times the impact parameter, and this improved sum rule precisely becomes the kernel of the Fourier transform that brings me from momentum space to impact parameter space. And so lo and behold, you just get the Fourier transform to impact parameter space. And so the condition that this be positive just translates into the condition that this function should be positive in impact parameter space, or at least this positivity condition in impact parameter space is a necessary condition for what you need. And so lo and behold, you need functions which have compact support in momentum space because, again, u is localized between minus m squared and 0, and they have positive in impact parameter space. And with those functions, which are actually plentiful, you're able to derive bounds. And so, of course, you find these functions by linear optimization. You put them on a computer. And this is a typical kind of function that you find. In impact parameter space, you find something that behaves a little bit like a step function. And that regulates the graviton pole divergence, because in impact parameter space, the graviton pole just becomes something that grows with B. And so the moment you have something which is a step function, that makes it, of course, converge. And conversely, the only way to get a regulation of the graviton pole is to be something which is localized in impact parameter space. Okay, so that concludes the technical part of my talk, and then we can look at some results. Are there any quick questions about this? Okay, if not, finally, after all this whole discussion, we get to look at some results. So these are exclusion plots. Here, for simplicity, I just look at the simplest ratio of G2 over the Newton constant, G3 of the Newton over the Newton constant, made dimensionless by absorbing a suitable power of the UV cutoff. These show curves in various dimensions, and they show, and these are exclusion plots that tell you what is allowed to the right. So everything to the left is excluded. As you can see, the exclusion plot become weaker as you lower the dimension. That's expected because Gegenbauer polynomials in higher dimension can be written as positive sums of Gegenbauer polynomials in lower dimensions. And what's interesting here is, remember, G2 was the coupling that Adams et al. Had told us had to be positive. And what's interesting here is that now this is allowed to be a little bit negative. So the inclusion of gravity actually allows for this higher derivative correction to be a little bit negative, and that has a physical interpretation because gravity gives you a Shapiro time delay. The scalar amplitude gives you the time advance, and you can balance them against each other so long as G2 is not too negative. Now you can observe, of course, that G2 has no upper, in unit, the ratio G2 over big G has no upper bound, but that's just an artifact of the fact that we look at this toy model of gravity, of a scalar coupled to gravity. And so G2 measures the self-interaction of the scalar, and big G measures the self-interaction of gravity. And in the absence of some further physical input, nothing fixes their relative ratio. So it's expected that this should go all the way down to the right. However, if we are doing the proper thing, which should be just scattering of gravitons, then the only physical coupling would be big G, and then you would actually be entitled to find perfectly compact regions. Now you may ask, is there something special happening at this corner? Is there some new novel theory of quantum gravity, much like in the Ising model, people were finding that the three-dimensional Ising model lives at the kink? And we don't know. So as often is the case in this bootstrap problem, the moment you sit at the boundary point, then you get to compute the whole spectrum. And so we can actually, we find this discrete spectrum, which we can compute. And it's very curious. You see, you find these Regge trajectories, but they go the wrong way. Right? In string theory, you have a leading Regge trajectory, and then the Regge trajectory will go this way. And so this is the converse of string theory, where you have Regge trajectory. So actually, it's completely unclear to us whether this is an artifact that will be excluded. Of course, these are just necessary conditions. It's entirely possible that it will be excluded by stronger condition, or where there is some exotic theory that has this behavior. And then by playing similar games, by depurating these sum rules in a more complicated way for higher couplings, you get to now find these compact regions for, you see, this is, what is it, G4 and G5, G6 and G4. And these are done for different values of this coupling that you cannot really fix. And the moment you zoom in onto the corner, these shrink down to tiny islands. Okay, so this was in this little toy model. Ideally, you like, and this is, I think it's entirely possible, just a technical issue. Ideally, you like to do this for scattering of gravitons. And as a shortcut to do graviton scattering, let's do super graviton scattering for the time being. So supersymmetry allows you to actually factor out the helicity dependence. So if you actually have maximum supersymmetry, you can reduce the problem to an effective auxiliary 4-point scalar amplitude, which is fully Croton symmetric. And furthermore, supersymmetry improves the Regge behavior, so that rather than having m over s squared going to 0, now you have s squared times m. So there are 4 powers of improvement. And so now we are just dealing with supergravitons. And so this G0 term here, as you're probably familiar with, maximum supersymmetry is such that that the leading correction is the famous R to the 4th coupling, right? In maximum supergravity, the leading correction is R to the 4th, and G0 up to some numerical computable numerical coefficient is the same as this thing here. And so now the question is, can you put a bound on G0? And rather in units, of course, you know, again, the only thing you can hope to bound is the ratio of G0 with G in units of the UV cutoff. And yes, remarkably, there is an upper bound, which is, of course, not too surprisingly obeyed in string theory. And this is remarkable because it's actually telling you on very general grounds, at least with supersymmetry, but I think this should really go through without supersymmetry. All interactions must shut down as the Newton constant goes to 0. Right? You could have imagined that if you take two gravitons that interact with some massive particle, the coupling by which that massive particle couples to the graviton could be arbitrary, but that's not true. As you make gravity weak, as big G goes to 0, then that coupling has an upper bound, and so it also must shuts off together with gravity as you send the Newton constant to 0. Okay, so let me conclude. We just look at the toy model, but it's clear that the general ideas are general. And so this is sort of the beginning of a program to bootstrap or classify or exclude, however, depending on your level of ambition, weakly coupled theories of gravity. And the key technical issue, which was this graviton pole, is solved by measure parameters at small impact parameter space. And I focus on the flat space story. The ADS story is in spirit very similar, technically a lot more involved, but the recent developments in analytic bootstrap, such as dispersion relations in Mellin space and related ideas, allow for an almost straightforward translation of this story to ADS. And there, of course, you have the advantage that these axioms are completely rigorous. And the first order of business is to prove that the large NCFT with large gap truly has a local bulk dual, in the sense that you find this precise suppression of the higher derivative couplings as you send the gap to infinity. And this is something which we think we can now do. Let me conclude here. Thank you.
Yeah, Leonardo, thanks a lot. That was a super nice talk. We actually have time for questions now.